Hello, everyone. My name is Saeed Masiha. I'm going to talk about our recently accepted paper at NeurIPS, which is a joint work with Saber Saleh, Niahi, Negar Kievash, and Patrick Tiran. This work is mainly about the sample complexity improvement of one of the stochastic second-order methods over SGD for gradient-dominated objective functions. I start with the definition of the stochastic non-convex optimization problem. This is a minimization of an objective function which is potentially non-convex. It is obtained by an expectation of an accessible function over some unknown distribution like PKC. We're trying to use stochastic iterative algorithms which have access to the samples of accessible function and its gradient and its Hessian at query points, for example, x. And we're trying to use this kind of algorithms in order to converge to epsilon global optimum. And here's the definition of the epsilon global optimum. And it means that the function value at the output of the algorithm, for example, at iteration t, is within some epsilon of the minimum value of the objective function in expectation with high probability. We're trying to get efficient total sample complexity in order to converge to epsilon global optimum point. And this is a number of queries of that triple of the function and its gradient and Hessian in all the iterations. And this NT epsilon is the number of queries per iteration. I'm going to define our desirable stochastic second-order method or stochastic cubic regularized Newton. I start with the well-known stochastic gradient descent. The update for a stochastic gradient descent is can be seen as a minimizer for some linear function in terms of delta, which is quadratic regularized, and this delta t can be calculable, and it has some closed form in terms of GT and eta t. GT is some gradient estimator, and eta t is the step size or learning rate in SGD algorithm. We can extend this approach to higher order, and a stochastic cubic regularized Newton or SCRN can be defined as follows. The update for this algorithm can be seen as a minimizer of quadratic function in terms of delta, which is cubic regularized. And in this function, GT and HT are subsample version of gradient and Hessian estimators. And this M is some replacement of that 1 over eta t. And in this algorithm, this M is constant, despite of SGD that has some adaptive learning rate. In order to converge to epsilon global optimum, we need some extra assumption besides some regularity assumption for our objective functions. And here's one of the assumptions that we use in our work. This is called gradient dominance. And gradient dominance assumption makes sure that all of the local minima of the function are actually global minimum of the function. And this definition relies on two constants, tau f and alpha. Alpha is much more important because in the sample complexity, alpha is important to show the sample complexity of the algorithm. And for alpha equal 2, this assumption is a kind of less restrictive assumption than S-triangle convexity assumption. And for alpha equal 1, there is an application for this kind of assumption, and a weak version of this assumption holds for a family of objective function in RL. Here is our result, and we prove that the total sample complexity of SCR and under gradient dominance assumption is as follows for different values of alpha in order to converge to epsilon global optimum point. And there is improvement of SCR over SGD. For example, the largest improvement here is for alpha equal 1. SGD for alpha equal 1 has a sample complexity in order of epsilon to the power minus 3, and SCRN has a sample complexity in the order of epsilon minus 2.5. And for alpha equal 2, they are same. And we use a variance reduced version of SCRN with time-varying batch size to improve the sample complexity of SCRN in the case that alpha equal 1 because of the application in RL. And yeah, we get some improvement for variance reduction when we use variance reduction in SCRN. And in policy-based RL, under the weak version of the gradient dominance with alpha equal 1, SCRN and its variance reduced version improves over the baseline sample complexity of stochastic policy gradients. Thank you for your attention.